We're going to do a quick review of SV input modes. We have two modes where a GTNet SV can read in an SV data stream. There's an interpolated and a raw mode. Also, the output mode can be a dual stream. And I'm going to show how to control the quality bits of an SV stream. So in January, I made this circuit here, and I'm going to use this. It's a very simple circuit. We just have a source and a fixed load, node voltages and branch currents right here. And we're going to output very similar to what we did yesterday afternoon. But the second SV component, or the second GTNet SV card in rack 1 will be turned to input mode. So we'll do a quick review again. We'll recap. We bring the GT sync component onto the campus, right? This allows the GPS clock to be used to synchronize the time step. The assignment of the controls processor. This is so important that you guys have to realize that. Let's say this is the simulator, this desk, and there's components connected to it. Component 1, component 2, component 3. But they're connected to different processors in the simulator. How do I know what processor this component is connected to? It's the manual assignment. So if there's a line here, and this is processor number, or card number 1A, and you want to make it processor number 1, and you're going to drop a component into it, you have to somehow identify this component with this processor. We've been doing this throughout the whole last training course and this training course. And again, if you don't understand it, we can come by and help you individually. Because I think some people understand it, some people don't. So, processor controls processor number 1 is connected, is going to use PD5 number 1, so the very first processor board, and it's going to use processor A or processor B. It doesn't matter. One of the two on the first processor board card. So this gives us controls processor number 1 that is going to execute code on the first processor board. So we have our identification here, right? Number 1. So on my virtual controls processor, number 1, I've been told to operate on number 1 processor A, right? So that means I can control any I/O cards connected to this board. Right? So, okay, so I'm processor number 1. Here's the first GTNet card. You take a fiber connection and go into one of the ports on the back, right? So now, when we put components onto the graph case, there's a link between what I'm being called processor number 1, the physical card, and the fiber connection into this card. That type of relationship has to exist every time that you connect into a GTNet card, a GTAO card, your GTFPI card, any communication, physical, like electrical or digital, into and out of the processors inside the simulation has to be done that way. So we have our identification of a controls processor being assigned a value of 1, residing on the physical PB5 card number 1, and it's going to be executed on the first processor. Okay, so now I want to use one of the peripheral cards connected to that processor. And we're going to use the GTNet SD protocol. So we bring our component onto the canvas, and then we supply the currents and voltages and we identify the physical card number and the fiber port number that the card is connected to. Okay? So this information, the card number and the fiber port number, can be taken from the configuration file. Or you can do it on your own by doing a telnet session and typing in RTDS-File4. We went over this last month in the training, or in January. So the general rack status, we have our GTNet SD. number 1, so this is GT fiber port 1, and it has an IP address, and here is the GTnet SV on GT3, so that means fiber port 3, and then it provides the information of software versions and IP addresses. So all of this configuration is stored in the configuration file. And this PB5-1 means PB5 card number 1. So this is our first GTnet on fiber port 1. So that component will be targeted to this GTnet SD, right? Fiber port 1, card number 1, processor card number 1 is all identified here, right? Fiber 1, processor card number 1, if we look down and we look at the rest of the circuit, here's the second GTnet SV. Again, it is connected to GPC fiber port number 3, but it is also assigned to controls processor number 1. Right? So you can have, each controls processor can handle very many different types of components. It's basically limited to the amount of executions required for each component and the amount of memory on the card. Now, for input mode, the GTnet SV is programmed to listen to a certain multicast address. In this case, we're multicasting our output SV to 010C CD 040000. That is the same address here. So this card will publish out onto the network, and this card will listen. So very same kind of concept as what you guys were doing with SD Scope late yesterday afternoon. here's a look at the plot. The black trace N1, so node voltage 1, is what is being sampled and then packaged into 9-2 LE information. And then N1X is that information that is being read by the second GTnet and then being put together back into the original waveform. Now, the two waveforms match really close because there's two different modes of input into the GTnet SV. There's a raw mode, and there's an interpolated mode. I believe this is the interpolated mode. So with that, the GTnet input buffers the samples coming in from the network and then does an interpolation and smooths out all of the differences in sample time. Now, if we put it to non-interpolated mode, with raw mode or non-interpolated mode, as soon as a packet is received, its value is put into the simulation. That's why sometimes there's a longer delay. It's kind of hard to see, but it's going to be down to the resolution of the timestamp. But if the simulation could run at 1 microsecond, we would probably see more jitter. But that type of sample jitter, it is going to occur naturally, right? Because you have no control over how fast the samples are, once they're onto the network, how fast they get into the relay. So that relay there is going to have to do some sort of smoothing or buffering and make sure that the samples are processed sequentially, and also do some sort of filtering, right? Did everybody get Wireshark working yesterday? Yeah. I just did a short capture here, and I'm going to look at one frame. So in the information that's put out onto the data frame, there's a measurement, and then each measurement has a quality part associated with it. And with Wireshark, the decoder of this information is already built in, so you can just look at the packet, and then if you want to expand and look at the quality, notice when I move between different parts of the measurement, it moves to the actual text value. So the quality part here, see it's 00, 00, 00, 0, 0, 0, 0. The GTNet can be set up in such a way that when you're running the simulation, you can control these different quality bits. So let's say relay X over here is supposed to do something when some of these quality bits are set. You could use the GTNet SD to publish the sample value data and then set the appropriate quality bit here and see what the relay does. Now, up here in the Ethernet, there's a source and a destination. So the source address, in that presentation that I did in the afternoon, the intro to 61850, we talked about how each company has their own unique identifier, first 3 bytes. Notice it says it was 0050C2. So RTDS tech, and then the last 3 is the physical MAC address of that GTNet card. The destination, see it says 010CCB 040000. This matches this multicast address here. And notice that it says IEC TC57. So the IEC Technical Committee 57 is registered to 010CCB. So there's 3 different groups of multicast addresses that they recommend to use. One for SV, one for IEC Goose, and then one for the older UCA message. the SV ID, this string here, is what is programmed in this component here. It's a combination of this LD, logical device name prefix, and logical device name suffix. And I think it uses MU in between the prefix and suffix. So if you change these, it should notice that the ID is now says Dean. So some SV relays, they do the filtering on this SV ID, and then some use this plus the multicast address. So it depends on each of the manufacturers. But typically it's this SVID and the multicast address. I think that the 01 is after the 00. Good try that. It's prefix, MU, suffix, and this sample count, while we're looking at it, we might as well look at this. Each packet that is put out onto the network, it will so if we're at 80 samples per cycle, and our nominal frequency is 60 hertz, we should have 4,800 samples, and what is going to happen is it is going to start at sample count 0 and then roll over at 4799. As you can see, there's just so much information that is put out on it. Okay, 4799. So there's the rollover. Sample count 0, 4799. So why don't we, I'll modify this draft case and show how to modify or actively change the quality information. There's output quality, output channel quality enables, and there is a question, no or yes, for each quality for IA, IB, IC. So each one of these channels has information being transmitted, and then you can override the quality for each channel. So if I'm doing IAQ, or I'm going to do channel IA, this is just a named variable that's going to be coming from the simulation. So the easiest way to do this is so now I have a switch which I can control any of the quality bits. I've provided the same name as what is required as an input. The input component by default publishes the quality that it receives with each channel, and by default it's creating an output with the same name. So I'll just change it. This switch here is going to make the GTNet publish some information with a quality bit set, and then this variable is going to be what the second GTNet is reading. So here's the first bit, and then if we look at Wireshark, so this is channel, the first channel, IA, and we set the invalid flag. Now, you could also set the test flag. So really, you would think that if your relay is receiving sample value data and it's in test mode, it it should probably not do any tripping or do any protection operations, or if it does, it should set its output into test mode as well. So to really know what an external device is going to do, you have to read the documentation and then see in the documentation what it does when this type of information is manipulated. And if it's supposed to do something, at least you have a way of manipulating the appropriate data in that sample value stream. So why don't we spend 15, 20 minutes or however long you want, do some practice on here.
บอกเป็นครั้งหนึ่งเซ็ตที่ก่อนที่อยากฟังต่อไปเลยมีเยอะ
Okay, we're going to continue on, and we're going to work on the example using the Alstom relay. So the case is in a subfolder called P444. So this is an existing case that was a double circuit configuration that had a source at one end and I think a generator at the other end. This is very similar to that script case that we used that had similar type of configuration. So it should be, it's not anything new that we're introducing. There's the configuration. The slight variation is we're integrating an actual physical relay to perform the protection and control functions on one of the circuit breakers. So what we want to do is set up the simulation so that the Alstom P44 line protection relay responds to the sampled values data and also communicates the IEC 61850 information to and from the simulator. So did we discuss how to make one of these boxes have an image? No? You did? Well, Cyprian says he showed you guys. If you edit and there's an image path, and in this case, there's an image that is overlaid on top of this hierarchy box. So do you see that? Yeah, okay. an SD component. We're taking the breaker currents, ICD2, ABC. So these are coming from, I'm assuming, circuit breaker number 2. And we're taking node voltages in 16, 17, and 18. So here's circuit breaker 2. And node voltages 16, 17, and 18. So it's on the top of the first parallel line. Now so we have our multicast address and our SDID. So this information is going to be used by the Alstom relay to accept this SD data. I'll open up the Micron software a little bit later. We also have an option here to include the sample sync field in the message. So this is another piece of information that's part of the data that says whether the samples are synced or unsynced. So we could set it to from true to CC, which means controls component. And in this case, right here, we just have a switch to turn the sync off or on. Our GSE component, okay, let's back up a bit here. We got GTNet card number 1 on fiber port 1, right? Because we just went through this, we have 2 GTNet cards, one on fiber port 1 and one on fiber port 3, right? The difference is we need to have 61850 GSE communication on the second GTNet card, right? But because we don't want 2 SVs, we want goose and sample values. So we need to figure out where the GSE card is in your hardware, and go through the process of putting GSE GTNet into rack 1. Okay. It sounds a lot harder than it is. Because remember, it's just a fiber connection, right? A fiber connection, and then changing the configuration file to match the new hardware in the simulator. So the quickest way to figure out where the hardware is, okay. So in rack 1, this matches, right? Because we have our AI, AO, all of fiber port 2. We have one SD on fiber port 1 and another SD on fiber port 3, right? So rack 2, okay, here we have a GTNet card on fiber port 1, right? The GTNet cards, when they're installed in a rack, they only communicate with the processor cards through a fiber port. The connection to the backplane in the rack is only used to provide the power to the card. That's it. The GTNet card could be sitting in the portables. The portable would provide the power, and then the communication to and from the simulator is through the fiber port, right? So we have a couple of options here. We can take the card from rack 1 and rack 2 and swap them, or we can remove the fiber connections. So, So we have this kind of a connection that exists right now. So remember, we could take, this is a card. We could move this card around. Or we can unplug the fiber. And then regenerate the configuration file. And now the appropriate firmware is in rack 1. So how about we do this? You in secret do your reconfiguration, and then we ask everyone else to figure out what to do. Okay. So you can mix it up.
Right. And one question that, so we look in the console that we then have the USB and then USB to the
Yeah. So here's our challenge. Professor Sudachai is going to reconfigure rack 1, but maybe not in this manner. He'll choose, and then it'll be up to you to tell me how to set up the draft case so that it works. Go, Pete. Can't come back. This is Kurt here.
ได้ได้ครับคุณครูได้ขอบคุณมากครับได้หลุดได้ไงครับ
Okay, racks 1 and 2 are now powered on. They went through the power up and diagnostic cycle. So each of the new configuration is there. Now, you guys have to tell me what steps I need to do to figure out what the new configuration is and how to modify the draft case to make it work. You guys need to fill in. Tell me what to do. No, you're not allowed to. Okay, the config file editor is open. Go here. Now what? Right here. Okay, so we did step 1, 2, and 3. So we have our new configuration in here. So what's next? do with this. I don't know what to do next.
Select Ethernet JSE. Keep select tab Ethernet JSE to select your port. Ready?
Okay. You want me to select GTNet? Okay, selected peripherals. We have GTNet GSE 3. So what does that mean? Okay.
Ví dụ là những cái vùng nón thì chúng tôi nón được này là
So, what other piece of information that is relevant to doing a manual processor assignment? Remember, we have 3 processor cards in your rack. So we have the fiber port numbers for the GT nets, but what else is missing? It could be any fiber port, right? But what is specific with the configuration about those fiber ports? Right.
One.
Okay.
One.
So the highlighted blue area, it says number one, right there. So that's processor board number one, PB5 number one.
Okay.
Now, he could have moved all of the fiber port connections to this number, number 3, or number 2, or a combination of 1, 2, and 3. But he was being easy and kept everything on processor number 1. So now we have enough information to do a simple change in the draft case and recompile. So even though at the beginning it sounded maybe a little hard, but in reality it's very easy. It's not that difficult, right?
I have a concern. We moved some hardware around. We added hardware into rack 1, and we removed hardware from rack 2. Should we fix up rack number 2 configuration? Not necessary?
Normally we use we have 6 processor. Maybe should be use separate in many cards to many processor, right?
It's better to keep all of the I/O on one card, because if you, let's say you have analog output on card number 1, and then front panel interface on card number 2, and SD on card number 3, and GSE on card number 5. That's 5 out of 6 being used just for input output. So you have nothing left to do power system simulations, because one card is required for the network solution.
It's better if we share the process to many processor.
You can connect the cards to different fiber ports, but those fiber ports can share the same processor and do all of the input-output functions and use only a small amount of the whole computing power of the rack, which allows you to leave the network solution and power system components and other types of models.
Welcome down to
always better to leave something open, because if you make your simulation and use everything and there's nothing left, and you forget something that you need to do, then you have to start changing all of your work again. So I've opened up the case and I'm going to compile. Okay. So now I'm stuck and I don't know what to do. So I need some help. You guys are customer support for RTDS right now. Yes. Yes. Okay. So when we get so many customer support questions on the same type of thing, people change things around, compile the case, and then say, oh, there's something wrong, and then without going through the process of figuring out what was wrong. And so you told me that the GTNet SD should be changed to a different fiber port, right? 4? Okay. Here? No. Oh, okay. I'm just going to hide what I'm doing because I'm going to put another error. Okay. So we have GTNet GSE on fiber port 4, and we have GTNet GSE on fiber port 3, right? So everything looks good, because we looked and we noticed that GSE is on 3 and we have an SB on 4, right? But I've got another error.
And the SI control processor is set to number 2, but right now it's stick number 1.
1A. Why? I'm brand new user, I don't know why.
Well, and the config file show that track 1, file number 1, this one number 2.
Okay. Okay, okay, so the case compiled successfully. What if this controls processor assignment was a number 2? Let's say I had this as number 2, okay? And I get another error. Do you know why? So I change this to number 2. Number 2. Okay. So now the case is compiled, right? If we want to look at our processor assignment, so because I just chose to put the SD and GSD on processor number 2, I've actually taken away one of the free processors because all of the other controls were still on processor number 1, controls processor number 1. So we can see our, we have our SV, Goose, our GT Sync, all on number 1, or no, processor PB51A controls processor number 2, and then all of the other ones were automatically assigned to a free processor. This is okay because you have free resources available, but let's say you actually needed more power system components and you did not have this third rack, right? If card number 3 was gone and you needed another controls processor to use more power system components, doing what we just did limits your ability to add and make a bigger simulation. So we could put the GTNet stuff back onto the same controls as the rest of the logic inside the simulation. So the case compiles. We'll see if the simulation actually runs. Okay, so the case was modified. You guys worked as RTDS customer support and got the case working, and it only took 25 minutes. You know, from reconfiguring, figuring out what to do, and realistically, you should be able to do this on your own and change the configuration however you want. And you know, because you do not want to look at those errors and then be stuck for 1 or 2 days and emailing us, and we're 12 hours behind you. So by just doing this and getting practice and knowing how the pieces fit together inside the configuration file and the simulation and the hardware, just allows you to, you know, work and use the simulator at your own free will. You know. So that was good exercise. But we're still not completely finished, right? Because we got to make sure that the relay works and look at the rest of the configuration of that network switch. And I think we'll do that after lunch. Or maybe after lunch, everybody can modify the copy of their case, compile it, and make sure it works.
ข้าวเที่ยงก็ต้องมาตอบทำไหมครับครับเฉลยว่าตอนนี้ผมย้ายการตัวเด็กตอนนี้เด็กมันอยู่แบบสองต่างการห้องเนี่ยบอกว่าหลายคือแล้วตรงไหนก็ได้ตอนนี้ไฟต่อเข้ามาจะต่อจะรู้เรื่อง
ร้าน
ตัวนั้นคือตัวที่ตัวที่ใส่มันเราให้เราใช้
มันแค่2 วันที่3
ตัวที่
อ๋อ
ใส่
ถ้าเกิดว่าเราแยกจานไอตัวสีฟ้ามันก็จะอยู่ทุก
จ่ายไปก่อนจ่าย
เพราะว่าถึงแม้
อันนี้มันมีว่าสีฟ้าถ้าเราจะว่าไปใช้อื่นอีกก็จะสีฟ้าก็มีที่อื่นอีก
มันก็ใช้งานเลย
ใช้ใช้ทั้งอันเลย
ใช้งาน
แสดงว่า
ถ้าเราจะเอางาน2 อัน 3 อัน
ใช้ทั้งอันเลย
สมมติว่าอย่างนี้ต่อไปก็ก็จะทิ้งการไว้อย่างนี้เลย
ดีอย่างนี้สุดละเพราะว่าถือว่าเราจะใช้ซอสน้อยไม่ดีนะเป็นอันสุดท้าย
อ๋อแต่ว่าสมมติว่าย้ายตัวการเนี่ยมันก็ยังเป็นก็ยังสื่อสารกันได้
ได้หมด
ก็อ๋อมันไม่เกี่ยวกับ
ใส่ไปว่าที่เป็นยูด่าขายแล้วต้องพยายามจัดที่ดี
ฟังนั้นตั้งแต่เมื่อวานนี้ทีเลยนะไม่มาเห็นเลยผมว่าเป็นการทบทวน
นี่จะทำอะไรจะฟัง
ดูไปแล้วเราจะเข้ากรณี
ก็คือชื่อก็จะเกิด
เพราะว่ามันเป็นคนละกรณี
คือการเพลงนี่ใช้เป็นเมื่อกี้ฟังเหมือนว่าการเพลงเป็นไปเรียน
ถูกต้องต้องการเลี้ยงเฉย
แล้วก็เพลงไม่ได้เป็นแบบว่าสื่อสาร
เฉพาะตัวจริงๆแล้วต้องดูดีเลยตัวนี้ก็คือการเลี้ยงว่า
ก็เริ่มจากว่ามันเพลงเป็นแบบว่าสื่อสารเลย
เพราะว่าในที่มันมีเกณฑ์ที่คือการสื่อสาร
ว่าฮะไปว่าเตะว่าฮะ
ประกันการเซ็นซีการสั่งงานของยุคนี้นะครับ
วันของเราเล็กเรามีอะไรมาเลยก็ถึงจะดีนะคนเชื่อว่าครับ
กับไปเอาไอ้ที่เราซื้อที่ร้านนะครับได้เลยจะเอาเลยนะหรือว่า
ตอมเมื่อกี้นี้ว่าจะเสือ32นี่เหรอ
กินข้าววันก่อนเร็ว
พี่ก็เดินไปช่วย วันสองทีอ่ะเบื่อเดี๋ยวจะลงตัวแค่ให้เร็วจะได้
ร้อยแบงค์
แบงค์ร้อยครับแบงค์ร้อย
มี800อ่ะมีแบงค์500ใบด้วยคือ500กับเรามี900อยู่แต่มีแบงค์500ใบไม่ให้นะไม่พอแล้ว
ไม่พี่น้องด้วยครับน้องมีครับต้องรู้ว่า
ผมเหลือจะเป็น100หมดเลย
น้องไม่ก็แบงค์ร้อยจริงๆต้องการแค่700ไม่ต้องการ700
ก่อนได้โดดได้ให้ทีหลัง
มีไหมไม่ถึงแต่มี900อ่ะ
เนี่ยเราไม่ได้โดด700เอาไปก่อนแล้วโดดให้เลยอยากเดี๋ยวต้องคิดให้มัน
อ๋อ
เก่ง
โดน700อ่ะมาเลย โอเคเลย ขอบคุณมากเลย
ไหนโดด
before lunch, we compiled the case. We modified the case with the new fiber port connections, and I'll just go through some explanation of the configuration of this logic and explain how the goose controls is mapped to actually control the circuit breaker. So earlier in the morning, we reviewed the sample value publication. So there's nothing different here. It's exactly like a simple case. The goose control GTNet GSE. What we have here is a couple other options turned on. There's a test, a global test bit that is part of the goose message. Now, the GTNet can publish 4 different goose data sets. In this particular case, only goose data set number 2 is turned on. And the global test to be activated for goose number 2, this switch here, GT2, would need to be turned on. There's also a needs commissioning flag in the goose message, and if that is enabled, setting the appropriate bit here would turn on the needs commissioning indicator in the goose message being transmitted. Now, goose number 2, we're taking STBRK2. So this is an acronym for status of breaker number 2. So the status of breaker number 2 occupies the first 3 bits. Okay. A phase is bit 0, B phase is bit 1, C phase is bit 3, or 0, 1, 2, right? Now, if we want to pack more bits into that, right, and this signal here, this other variable, is only a logic 1, 0 or 1, to make that bit number 4, you have to shift it over 3 positions, right? So now we've bit shifted behind the bits that are being occupied by STBRK2, right? And for some reason this is a fixed 1 and it's being bit shifted. So you combine all of that, and now this variable here, tx2b, now contains a potential, 5 bits of information. So what we're going to be doing with the status of the breaker, and this is the permissive trip or the carrier send from line or breaker 1 at one end to the relay, that physical relay there. So the Alstom relay needs to be configured to take the status of the breaker and the carrier send and put it into the appropriate logic inside the relay. Okay? Goose in is a 32-bit integer, and this information is programmed by you using the SCD editor. Okay, so because it's a variable 32-bit, you have to put the appropriate goose message into the appropriate bit location, and then program your logic inside the simulation to do the correct thing. So let's go and find goose in. Now, I could easily go and find it because I know where it is in the logic, but a quick way to do it is to copy the characters and then do a find. And now it comes up with the 3 different locations inside the draft case. And selecting either one of the 3 automatically moves the draft into the location of that variable. Okay. So goose in we see we're bit shifting information bits. Anything past bit 8, we're bit shifting, and that's the information that we want to use. So I'm looking at this logic here, and it seems that we start a timer on the start of the fault, and then we stop it when we receive some information from the relay. So this must be a timer that times how fast the relay responded after the fault is applied. There's another bit being used, and it's going through a pickup timer, and then it's being sent to the other relay. So this must be the communication or permissive trip. The other goose in is going into this breaker control, and this component is a controls component that has a bunch of different features and timers that that control the operation of the breaker. So there's a trip and a close signal. So if we open up the breaker control, it's set for single pole tripping. There's an enable of external trip and close inputs, which is these right here, external trip and close. The breaker status, the initial condition is closed, And then there's individual timers for each phase of the breaker. So these timers emulate the operation, the travel time it takes to open and close the physical contacts of a real breaker. Now, the trip and reclose input and status, because it's set for 3-pole tripping, it asks which bit is going to trip A phase, which bit is going to trip B phase, C phase, a general 3-pole trip, and then a reclose. So by putting in the bits that you want to use that are inside this 32-bit word, it extracts bit number 9 and trips A phase. Bit 10 will trip B phase, 11, 12, 13, so on. And then the control, this goes and controls the breaker inside the simulation, and then this signal here is just generated to make the runtime interface when you actually see the breaker open, it changes color. That's all this is for. So remember, goose inputs, 9 through 13 we're going to be using, right? And then bits 1 through 4 we're going to be using inside the relay. Right? So this is information transmitted to the external device, and this is information coming from the external device. There's generally 2 ways of putting together the logic for this. You either start at this end and program the logic inside the RTDS to do what you want, or you start at the other end and public or create the goose information from the IED and then transfer it. So you either work one way, go this way, or work this way and go that way. If you start in the middle and go this way, you're probably going to have a problem. Do you guys remember from the first training course how to start the SCD editor? So this is the GTNet GSD component. When you right click and you go edit IEC 61850 SCD. So there's 2 options. When a file that's associated with this component already exists, you can open it up and change it. If there is no configured file, then you start from a template. So when the file exists, it's a name. Where is it? It's a name for a parameter here. The parameter is fname, basically file name, right? And then this is the name of the substation configuration description file.
Back in my day.
Yeah, it's good. So this is what the file looks like inside our editor. Here are the 32-bit inputs that are part of that variable that we call goose in. Remember we said we're going to use bits 9 through 13 or 14. So just by looking at the name here of the external reference, I can tell that it's coming from the P44. We also had a Schweitzer relay in here if we would have used the physical relay for the other end, but we only have one relay. So this information was just left in here. It's not really doing anything. So down here are all of the IEDs that are contained in this SCD file. So there's our GSE or GTNet. There's the data set for the 421 and then the data set for the P44. When you start from template, the only thing that is in here is the GTNet. To get the other files in, you have to do an import. So later on, I think this afternoon, I want everybody to rebuild the SCD file. So expanding the data set, we see our, remember yesterday we talked about the goose control block? Right? This is the data set items in that goose control block. And the information regarding that goose control block, here's our VLAN ID. We talked about priority, and then the multicast address. There's an app ID. Remember the heartbeat we talked about when everything is steady state? There's a default retransmission time. That's what is right here. There's a configuration revision, and then another thing called GUID, and it's a character. It's similar to the app ID, except that it's a character versus a hex. So getting these bits of information into here, you select what you want. So typically you're going to select the Boolean, and then you drag it. So you select it, press down on the left mouse button, and while you're dragging it, it's saying, no, no, I can't go here. No, no, I can't go here. Oh, I can go here. Now, if you wanted the quality also to be part of the Gaussian, you would select the quality and then drop it into the appropriate. On this action side, it keeps a list of everything that you've done, and if you want to quickly get rid of it, you can go up to the top and suddenly it's now the GTNet, the Goose output, each output, there can be up to 4 different data sets right now, and each output has its own unique parameters. So the VLAN ID, the MAC address is GU ID. All of this information is going to be used by the external devices. Just like we use information from these external devices to program the inputs. So this is a MyCom studio similar to what we used in January when we had the distribution relay here. If we look at the logic, I'm going to double click on it. So there's green input and output, and yellow goose in and goose out. So this is how you set up the logic inside the relay to get the goose out or the goose in. So we can see here that any trip from A phase is going to set goose output number 1. So this number 1 depends on the individual relay. I can't remember details like that. But the Schweitzer has quite a large number of inputs and outputs. So this goose out number 1 is right here. So P4 GGIO2 IND1. So this is any trip A phase. Number 2 is any trip B phase. Number 3 is any trip C phase. 4 is our 3-pole trip. 5 is our automatic route close. And 6 is our distance signal send. Right. So we put those into bit position 9, 10, 11, 12, 13, and 14. And if we look back at the logic, we see positions 9, 10, 11, 12, 13, right? And then 9, 10, 11, 12, 13, 14 is our carrier set. Right. So I've opened up the settings file here, and we looked at a setting block here called Ethernet NCIT, non-conventional instrument transformer. There's a physical link. Remember on the back of this relay we had fiber or copper. There's a logical node arrangement. And then remember I talked about this prefix suffix thingy? So this is the only thing that needs to match for this relay to take in that ST stream. If I changed it to DEAN 99, it wouldn't work. So here's our EMD1 and then 01. EMD1 MU0101. Okay, so there's actually a third thing that you got to do inside this relay. You have to do the 61850 configuration. And this is part of this MCL tab. So the 444 publishes its goose control block ST, and notice everything has this kind of lock symbol. You can go in here and edit it, and then you can change these parameters. So setting up the publishing is pretty easy. The subscribing, you have a map input. And here's our 32 inputs. So if I select this one, I can see that I've already did the proper goose identifier, and here's my data set reference. Doing this, getting this set up, what you actually have to do is for each one you have to browse, and then so this is the SCD file that we created in RTDS. So this contains the information that we're publishing from the RTDS. So you open this up, and then choose the appropriate there's a quality and a status. Now, because remember that that SCD file had the GTNAND, it also had the 421. We could actually program this to listen to a 421 if we had a 421. And then there's, once you get this all set up, then you have to actually send the configuration to the device. And I think you can only do it through a serial on the front port. Okay, so the simulation is running, and I've got a meter here for the megawatts and the megabars flowing through line 1. Remember, our all-stub relay is connected into here for breaker 2. And if I do a measurement, here's my MVA magnitude V1 and I1. I think you can actually add watts and bars and a bunch of other different information in here. So we can see that the relay is actually accepting the sample values. If I stop the simulation, I'm not sure if you guys noticed, there was the alarm light on and a bunch of other stuff flashing. I think everything is
Now it says juice is absent because I disconnected the Ethernet that's containing the juice information. So it's back to normal. Yep. Just take that off. Okay, so we'll do a C to ground fault.
close function is in there. We can try it again. Nate?
Yeah, okay, yeah.
Oh. I think that the recloser needs to cycle through its lockout and go into reset, because we started the simulation that had no breaker status, got the breaker status, and then 10 seconds later we put a fault, so it went to lockout. So.
Instead, I think it didn't come from reset.
Well, I had the simulation stopped, so there was no boost messages. Can try it again.
Yeah. What is alarm LED here? The last one, 1, 2, 3, 4, 5, 6, 7, 8. RTDS-L.
I'm not sure.
What is alarm here? Okay. Here is 7. At the right side.
Reset lockout.
That's LEDมันsymbol of LED and red and green. Yes, red and green color. Yeah, like that. So here.
ใช่คนนั้นขวาพี่ขวา
เหมือนเป็นฟังก์ชันของตะเกียงมี
Yeah.
แล้วมีตัว
Maybe the right side. Yeah. Number 7. Now it's blocked out because the telephone didn't. Okay. It's right. ก็คือ
รีบเลยอ่ะ
หลอดนี่มันปิดเพราะว่าเราตัวเลขว่าเราออนตัวเลขว่า is on ยิ่งตัวเลขว่า is off LED is not green.
Okay, try again.
Chip, ê,
ไม่ใช่ว่า
มันจะได้ไม่ได้เปิดเผยว่า
เซตติ้งเป็นนี้เช็คได้
เขาที่เขาตั
น่า
ด
จะ
เป็
เป็น
น
ที่เดียวแล้ว
เออ
ก็คือตอนนี้ก็คืออยู่ในสมัยหลังยูทูบใช่ไหมเวลาที่ทำงานเนี่ยเวลาที่แนวทำงานทุกอย่างจะแบบจะเป็นลายฮาร์ดไลน์แนวก็ไม่ได้มีแต่ว่าเราไม่เข้าใจเราไม่ได้เดียวได้ทำที่ต่อที่พูดเลยโซ่แบบก่อนแล้วก็มีอะไรมีอะไรที่ประชาชน
I've got the test mode set. That's why it's not working. So remember we talked about the test mode? So I'm transmitting the breaker status, but I've told I've set the test mode to true. So the relay is ignoring the goose. See, I forgot I was put a trick in and I forgot what I did. So. Well, yeah, it's not the test in the SD, it's the test in the goose message. So it's ignoring, that's why the breaker status is never valid. Yeah.
คือว่าในตัวนี้มันจะมีความคาดหวังว่ามันเป็น SP จริง SP หรอกมันเป็นอะไรเหมือนว่าไป test mode แปลว่าเราสามารถ test ขณะที่ใส่ไปนะที่ง่ายๆมันไม่ได้ส่งไปที่เป็นจริงนี่คือว่าส่งแค่คุยของตัวบอกไม่เกี่ยวกับโค้ดจริงอันนี้มีข้อดีว่ามัน test ออนไลน์ได้แล้วต้องระวังอะไรนะระวังอะไร
So data grounding. Maybe get us started.
Now it's not closed, right?
Maybe just clear it. Ah, okay.
ต่อเสียงตรงนั้นนะแข่งสองครั้งที่ครั้งเดียวแล้วก็ต่อไปครั้ง
25%.
Show me for the waiting time for the pick up from
19 motorcycles.
So far.เอาอะไรที่เกิด
Let me know when it's not always the same. Like you need that 2% can break every 100%. You need that.
Yep.
Okay.
Well, as long as the test mode is not on.
เราอยู่ในเทสโหมดนะ
When I contact them,
One second.
ที่ไซต์อเมริกาเนี่ยมีสับสเตชันที่ใช้พูดว่าเป็นIs there any substation in have use that also percent run that is there
I don't know. I haven't worked in the utilities since 1999. I know one of the substations that I worked at a couple years after, like I think in 2002 maybe, they started putting in Goose for doing the control, like the switch, like the operators would select the breaker, disconnect, and do all of that. But I'm not sure if it was actually coming from a protective relay. I know that the utility in our province, they have some substations that have been completely 61850. And some of the people that I worked with that were doing the engineering part of that, they were using Goose for everything. I'm not sure about sample values, but definitely Goose. But as a whole, I don't have a lot of knowledge of other utilities throughout the U.S. that are doing Goose completely. Southern California Edison is doing a centralized remedial action scheme using Goose throughout the whole network, and they're taking the Goose messages from all of the substations and then taking them into centralized location, and then they have a computer, like a centralized computer that processes all of the Goose message and then does all of the analytical decision and then sends out the Goose message to all of the different substations telling, and then they have the relays there that are programmed to do the appropriate tripping or blocking, and they're actually using the RTDS to test that system inside their lab. They have, I think, 14 GT nets and 20 racks of hardware. And they wanted that VLAN priority tag to change dynamically based on what was going on. So we've been actually changing the firmware to make it more generic so that they can program and use the RTDS to do things like that. It's pretty interesting what they can do. And then Dominion Electric in the state of Virginia in the U.S. They're doing an upgrade and they're purchasing 16 more GT nets. I'm not sure what they're going to be doing, but they've put phasor measurement protocol into all of them. So they're going to be doing some other wide area scheme testing. So how about you guys do a bit of work now? Why don't you guys delete? Maybe not delete this file, but create a new one and see if you can get it to do the same operation as before. I've got the ICD file for that relay, so you should be able to do the file import and then program the inputs. Okay. So I want everybody to copy that CID file onto your computer, and we're gonna go through this, okay? Because you're gonna have to do it, and it's better to do it now while somebody's here to help you. Okay. Right here. To finish off the day, there's a number of different examples of simulations that I included in your folders. The first one I want to show is this. It's a folder in the name called Exciter Sync. This simulation is actually quite interesting. It has a synchronous machine. We have our governor turbine, and then we have our electric field being produced through a exciter bridge. So what we're doing is starting the simulation up, and we have no field voltage. So the machine is just spinning, but it's not really generating any voltage. And what we end up doing is taking this field breaker, and basically we have a DC battery that we flash the field, so we get the field to start self-generating, and then once you flash the field, there's enough voltage here for the generator to start self-exciting, and then the terminal voltage here is controlled or converted from AC into DC through these firing. And what we take is just a very simple exciter model, and create some firing pulses through this TI controller. And initially this breaker is open. So once the exciter builds up enough voltage. The generator is sitting here near synchronous speed. And remember I said that that breaker control component does a lot of other things. Here, instead of using external trip and close, we've got a sync check function built into it or enabled, and we're taking node voltage 10, which is basically the high side voltage after the unit transformer, and then taking node voltage 13, which is the system voltage across a unit breaker. So the system will start up. If you press the control to send the close signal to this breaker, this component will seal in the close command and then wait for the two systems to come into synchronism, and then it will close the breaker, and then you can set the power order in runtime and ask the generator to start producing power into the system. There's 6 steps here that are part of runtime, so you can basically compile for one of the 4 racks and start it up and see what it does. So it says start the case, have the block, D-block in block. Close the field flash switch. Open or wait for the voltage to build up and D-block. Open the field flash switch. Close the push button over here and then wait for the breaker to close. Here's the voltage at the generator bus. Absolutely nothing, right? Close this. D-block. Open. So our voltage is going to stabilize here. If I press close, closes in. And set the power out order. And now we see the T for machine 1. We got 45 megawatts out. That's it. It's doing a lot of stuff in there, and you know, it's kind of nice to see that, you know, this is how a generator would actually be brought online, or an example of how one would be brought online. under example 14.2, there's so if you have Condor's book, and I think it's chapter 14.2, there's this is the network from his example. We have a source here, transformer. We have 5 transmission lines connected in parallel to this, and we have this generator here. We have this generator here. We have a load here. We have another load here, and we have a transformer with a tap changer. So what actually happens is the system starts running, and then with this load level number 2, we open up the breaker here, so that because of the power transfer, this bus voltage drops, right? And the excitation control here starts being overloaded because this generator is trying to maintain the bus voltage, and then this tap changer starts tapping, and everything gets out of control, and eventually this control here reaches a maximum field current of 3.02, and once it does that, then it limits the field current, and once that happens, then the voltage on this bus collapses, and the tap changer just keeps going. So it takes about 300 seconds or something like that. I forget. It takes a while, but you end up getting pretty close results, almost the same as what you see in his example. They're not going to be exactly the same, but they're close enough for me. So here's the reference paper, and there's instructions on what to do. He's very famous in stability control. I think his first name is Trevor. So you start the case. It says wait for some time, 30 seconds to a minute. You unblock the tap changer and then switch out one line. So it's going to be this control here. It's going to open up this line, and then you wait and watch for the voltage collapse to occur. When the voltages at the bus are approximately one per unit, then you would do this. So we see our field current here sitting at the pre-collapse condition. What I'm going to do is first I'm going to lock the plots here. I'm going to de-block the tap changer. The reason I'm going to block the plot update is because it's 300 seconds of data, and I want the 300 seconds of data request to come when I open up the breaker, not when I unblock the tap changer. So I'm going to now let the tap changer start, and then I'll open. So this line is open. You can see the field current in the generator jumped up. Now the control for the tap changer, the very first tap takes, I think, 20 or 30 seconds, and then subsequent taps happen a lot faster. And we can see our field current for the generator going up. And it's going to keep going up because the tap changer's trying to maintain the voltage here, which ends up causing the field current in this generator to reach its limit. And then once its limit is hit, everything falls apart. I didn't make this case. We had a visiting professor from Durban University of Technology in South Africa, Dr. Bruce Rigby. He was in our office, and he put this case together, and then I took it and tried readjusting some of the values of inductances in the transformers and got it. I just basically fine-tuned it to get it to look exactly like the plots from the textbook. So 5 minutes of plot data capture is kind of boring to sit here and wait for it. You can imagine trying to fine-tune this test case and having to wait between like 5-minute intervals to try a different parameter. generator was at its maximum for too long.
ที่มัน
Now
ฟังก์ชันมันบิวอิน
it's dropping, and now our tap starts trying to tap up again. And then here's our voltage dropping. And eventually, I think, yeah, the 33rd tap is the maximum. In this example, there is no RX plots, so I don't have any signals to do that. So here's all of the voltages at the different buses. Here's the field current, the Q, and if you're familiar with that example, and you look at the plots from the textbook and compare them to this result, they'll match. This inter-area oscillation one, I think what's happening in this system is you have a bunch of generators on one side, separated by transmission lines. So you have your impedance between the two areas, and you have machines with different characteristics, which ends up creating inter-area oscillation between the dynamics of the machines that are separated by the system impedance and the power system stabilizer. These are tuned to damp out the inter-area oscillation, and when you turn them off, you can see the system start to become more and more unstable. So this case is, there's not too many instructions. Actually, there's no instructions. But I think essentially what you do is the generators are sitting here running. You have all of the power system stabilizers on for the 4 generators. If you put a bus fault on, it applies a fault and then removes the fault, and you can see speed or the voltage is, the system is pretty stable, right? Everything, you see a big disturbance in this, but it's going to damp out. So you have the machines that are blue and green are out of sync with the machines that are green and or black and red. So that difference in frequency is the inter-area oscillation between the machines. And pretty much every system, electrical system in the world has this, right? You have different modes of oscillation, and it's classic stuff that utilities around the world try and figure out what their modes of oscillation are between different operating areas. So if I turn the stabilizers off, actually those two were off. So if I turn them all off, see the P and Q start swinging. If you keep doing a refresh, you can see the oscillation is just going to grow and grow and grow. So your distance relays on your transmission lines are going to start thinking, hey, something's going on. And start tripping lines and doing all kinds of things. So, in the power swing, there's a couple of draft cases here. There's also a README file associated with this power OCI file. And it talks about the oscillation mode, and what in this example you can change the inertia, the H of the machine, and you can get different, that will create a different mode of oscillation. And so you can, just by adjusting the H and following these instructions, you can see how you can vary the small signal oscillation in the system. So I believe this is actually from the generator tutorial, I believe. So, and what you're doing is actually just changing the inertia in this machine, applying a fault, and then getting a different swing between the generator and the source. This other example, it's using a source connected to another source through a pi section. So this is just providing some impedance between this source and this source, and this control component, this control circuit. We have a timer here that when you start it, it just starts incrementing the time from 0. We take that time, multiply it by 2 pi with a frequency offset. So this will essentially create a hertz per second rate of change. So what you do is you take this and add it to a fundamental frequency, and then you put your signal into a 0 to 2 pi ramp. So this 0 to 2 pi ramp is sitting here at nominal 60 hertz. You press start, and then the frequency either goes up or goes down at a specified rate of change. Now, this signal, 0 to 2 pi, goes into this three-phase waveform generator. And you can set the gain, so I set it to 230 kV, and then it goes into the source. So this is the same source that we've been using in all of our other examples, except we're defining the magnitude and frequency ourselves. This signal over here is connected to the other end. So by doing this, we basically have one system that is fixed. We start off with the two systems at the same fundamental frequency, and then we start the change, and then we slowly change the frequency of one end versus the other end, which is going to cause your power swing, and you can actually see the trajectory of the positive sequence impedance. What I'm using this sequence impedance calculation block, and it's taking in the node voltages and branch currents, and then we're plotting the positive sequence on an XY plot, and you see it. It just comes right through this impedance, and it's kind of good to see what would happen in the power swing, but in realizing, this kind of thing is how engineers set up power swing blocking or tripping, by being able to measure the speed of the impedance changing. So everything's locked here, so try 2. So here's our impedance magnitude, 4,000, somewhere way out over here. If I press, okay, here I've got 2.5 millihertz per second rate of change. This is our XY plot thing that we worked on. Oh, here it is. And so eventually this impedance will start increasing, decreasing, increasing, decreasing, because it just keeps swinging back and forth. So you can see that the frequency hasn't really changed that much between the starting, like 1.5 hertz difference, but the power swing between the two systems is just there. This one won't take very long. I know it's 4 o'clock, but this is kind of interesting too. It's a volts per hertz example. And so we're taking time here, similar type of thing. We're doing an adjustment of the frequency going into our 2-pi ramp here, and then we've got a transformer set up with some saturation. So so we have our start signal. We have time here. We've got our per unit voltage and an offset of voltage, which is going to give us a change in volts per hertz, right? So what we do here is per unitize the volts per hertz signal based on 60 hertz at 230, and then the volts per hertz signal goes through this logic here, so I have a limiter. So you can either press stop, or the system will automatically stop at this, when it reaches this limit, and then it comes back and stops the change. Now this example is kind of neat because you can run the system and then keep doing a plot update, and if you're monitoring the flux and the magnetizing current, you can see the system, the transformer go into saturation. I started, everything looks normal here. Notice the current of the transformer is starting to get distorted. Well, that's it.
We're going to finish up the course by doing a little bit of a program that we call C Builder. So, as you know, we have model libraries which have all sorts of different models for power system modeling. But if there's a model that we don't have, we have a utility that lets you build your own component. So we're going to do an easy example this morning of a multiple input adder, and I'll walk you through that. You can build two types of components in C Builder, either a controls component or a power system component. So this adder is going to be a controls component. It's in the tutorial manual, which I'll show you, and it's one of the easier examples. To do a power system component is a bit more difficult because you have to interface with the rest of the power network. and you have to have knowledge of the Donwa algorithm and how that works. So the controls are a little bit easier to handle. So we're going to build a model that looks something like this. We're going to have options for 2 or 3 inputs. So if we had a 2-input adder, it would look something like that. We have the model in the library, but we're going to build it this morning. So we'll have some variables. We'll be calling this input 1. This one will be input 2. And we'll call this output. And then we're going to have another option to have 3 inputs. So we're going to make the component so that you can choose between 2 and 3. So if we choose 3, the component will draw another input. And we also want to make it so that we can either add or subtract. So depending what we choose, these this might turn into a subtract sign if we choose inside the component to do subtraction instead. So we'll basically be drawing the component and then creating. When we open a component in Draft, there's a menu with different selections that we can make. So we'll have that menu and we're going to create things inside that menu in order to choose whether we're adding or subtracting and how many inputs we want. So we'll need some variables. First, we'll need a variable to keep track of the sign of the input, whether it's add or subtract. So we'll have 3 that we'll call sign 0, sign 1, sign 2. So that's going to keep track of whether it's positive or negative for add or subtract. We'll also have a variable called number of inputs, num inputs. It'll be either 2 or 3. And we'll have these 4 variables, 3 for input and 1 for output. So I'm going to lead from the front and everyone can follow what I'm doing. So I'm going to start by opening RSCAD. And you can see here we have a component called CBuilder. I'll just show you quickly in Draft. This is our adder component here. If we look at it, we're going to build something that's similar to this. We'll have the sign of each input and number of inputs. In the tutorial, we're going to do it a little bit differently than this, but the same, once we do this one, you can probably recreate this adder the same way. So everyone can open CBuilder, and I'm going to choose new component. Excuse me. We can choose the type of component that we want, whether a controls component or a power system component. So this is a controls component. So I can click OK. I'll give these guys a second to turn their laptops on. Everyone ready? Okay. So the first thing I'm going to do is save the component like we do in draft and runtime. It saves it in a directory called ulib, which stands for user library. So these are components that the user is creating. So I'm going to name it mult adder. So it's going to tell me that I should have some graphics if I want to use the component, which is okay because we're going to create them now. So you can see here you have a drawing area to draw a picture of your component. We have several different tools, zoom in and zoom out, tools to draw rectangles or squares, arcs, circle, and lines. You can also add an image if we want, or put text in the component. And then this last button here is for an I/O point. So we'll have to add inputs and outputs to our component. So the first thing I'm going to do, I'm going to draw the graphics that will always be there. Some of the graphics are what we call conditional. So depending on the number of inputs, if number of inputs is 2, we'll only have 2 inputs to the adder. If it's 3, then we'll draw an extra input. So I'll start by drawing a circle here. So this one is draw a circle from the center. So I'm going to start in the center here and make a circle. I'm going to zoom in a bit to see what I'm doing. Next thing is I'm going to draw a line for the input, for the 2 inputs. So this is the line here. So you can see it's snapping onto the line or the dots. So I don't really want that. So what I can do to remove something that I just drew, you can see over here we have action, new line, new circle. So if I click up here on new line, I go back a step and I can delete my line. So here I have snap to grid. I want snap to shape. So then I can pick my line again. Start here. And now I have my line connected to the circle. I'll draw another one. And one more. I also need a line for my output. And I want to make plus or minus signs. So we'll start into the conditional graphics now. There's a tab here that says graphics. So this is where I want to be. So I've drawn these things, and all of these will be there all the time in draft when we load the component in. So I'm going to add a condition. Actually, before I add the condition, I'm going to create some variables in here that I can use to make my conditions. So we call them parameters. So I'll add a parameter. Here's the information that I need to specify. I'm going to call it num inputs, like I showed up there. So what value should this be? Should it be a real, name, toggle, integer? What should I use? Integer, yeah. What should my default value be? 2? Minimum? Minimum value for number of inputs. 2, yeah. And maximum? 3. So here's my variable down here. I want to put it above everything else here, because typically when we open a component, we always have the processor, assigned controls processor, priority, and card type, and they're usually on the bottom of the menu. So I can scroll over here and move this up. So now it's on top. So this whole here is a section. So this section corresponds to one tab in the component. So at any time, I can click preview on my component, and I get this. This is the menu that would come up in draft. So I've got my number of inputs, 2 and 3. Assigned controls processor, priority, and card type. I want to add another tab here to so I can select whether I'm adding or subtracting on each input. So I'll go back to design. Here I have add section, and I'll say controls. So now I have another section down here. If I preview, there's nothing in there yet. So I'm going to add 3 parameters: sign 0, sign 1, sign 2. To add the parameter to controls, you have to make sure, if I'm selecting configuration, it will add it here. But I'm going to select down here, so I add them into the controls tab. So I'll add another parameter. I'll click sign 0. So I want to do floating point, so I'm going to use real. I'm going to use a real type of variable, so I'm not just limited to integers. Actually, I'm lying. I want to use a toggle. I want to be able to select add or subtract. So this is my toggle entries. Entry 0 will be add. starting value, entry 1, subtract. And that's okay. So now if I look in preview, I have a controls tab, and I can select add or subtract. So we'll have to remember that when sign 0 is equal to 0, that means we're adding. Or if we choose add, that means sign 0 is equal to 0. If we choose subtract, it means sign 0 is equal to 1. So we'll remember that when we write the code for the component. I'm going to do the same thing for sign 1 and sign 2. Add parameter. Sign 2, sign 1. Toggle. Add. Subtract. 0 and 1. I can click on this pin here like we do for plots, and when I click add, this window will stay open. So now I can add another parameter without reopening the window. Sign 2, toggle, add, subtract, 0, 1. So here we have an enabled condition. So we can write a if statement to see whether it's allowed to be available for us to use. So this is sign 2, which corresponds to a third input. So my enabled condition is going to be if num inputs equals what? Yeah. So now if I preview again, I can't, it's gray, so I won't be able to use it. I change number of inputs to 3. That didn't work well. I guess I don't need an if statement. I can just say the enabled condition is when num inputs is greater than 2. Okay, so now it's working properly. So it's available now when num inputs is greater than 2, but when it's 2, I can't use it. Okay, so that's, I think that's all the parameters we need in this section. So now we want to make our graphics depending on what we've selected for the sign of the input. So I'm going to say add a condition. It's going to be an if statement. So I'll have if num inputs equals 3. Then I get this little statement here. Make sure I'm clicking on it. And I'm going to add a third input. So again, now when I preview my component, num inputs is 2. When I say 3, I get my third input. So you can always check every step of the way to make sure that you're doing the right things. Now I'm going to make another input, or another if statement. So if sign 0 equals 0, then do I want to put an add or subtract? Which one? Add. Okay, so this isn't going to look very good, but you can make yours look better than mine. There, that's almost okay.
We draw by specify your position like y -1. I mean, I can specify the
Oh.
position of line at the right side and the detail and the table.
Sorry?
Can I modify the table on the right side?
This, which table? This table?
Yeah. That means I can modify the x, y position.
Yes, yeah, yeah.
But you know, when the programmer is for draw
Sorry?
ก็จะกลับว่าเขียนสีแดงออก
I mean, if the programmer cannot draw the perfect,
Okay.
so they can.
Yeah, I think so. When I'm selected down, here's the coordinates. So you can enter if you want. So I want to also make it, I want to make a minus sign if the sign is 1. But since there's only 2 options because it's a toggle, I can add an else. And I have to draw the line over the line. It's not very nice, but I'll just recreate this line. So now, if I preview, I have my plus here for add. If I choose subtract, I have a minus. So I'm going to do the same thing for the other 2. So sign 1 is input number 2, which is here. And then again, I'll say else. Draw another line. Save. Now I can make another if statement for sign 2, but I already have one. So I have this, if number of inputs equals 3, then I have this line here. So I'm going to put another if statement inside. So if number of inputs equals 3, I have these two lines automatically. And then a second if statement, if sign 2 equals 0, then I want an addition sign on the bottom. Else that. So if I save now, in my preview, there's my two additions. Subtract, subtract. If I enable the third input, add, subtract. So my drawing is basically done now. The last thing I need to do is add I/O points. So this is the I/O point. I'm going to put it, it doesn't like. Sorry? I guess so. You know how I can't get this thing to. The I/O has to go on a grid, right?
Starts at 0,
Yeah.
and then 32, 64, can't go halfway.
And what? No halfway. Okay. So I'm going to have to modify my lines here a little bit. Okay, so this looks terrible now, but it'll still work. And then I believe that one's okay. This is why I don't write models for RTDS. So I'm going to take an input here. I'm going to call it input 1, signal input, and which one? No, real. If you remember, in my parameters, my sign, no, it is a choice, but I'm choosing real so that we can add with decimal points. We could do integer too. It's really up to the user. So my second one, input 2, signal input real. Third one, input 3, signal input real. And here, I'll call it output, signal output real. So that's all the work you have to do for the component. Our I/O points should show up right here, which they do. So now we can write the code for the component. There's a tab here called C file associations, and we're going to make a new one. I'm going to call it, this name can be a different name than what you save the component as, but I'll use the same one. So now I have all my different parameters and inputs and outputs that I can work with in my code. I'm going to click on the pencil here to edit. So I have some different sections of code. I have static, which is where I'm going to declare my variables that I want to use. So I can declare some different variables. Gram functions is, we won't be using in this example, but it can call different functions that are available to use. So there's a RAM section too. This code goes through once before the simulation starts, so it can initialize any parameters that you want to use in the simulation. And then our actual code, which runs on the RTDS every time step. So I'm going to declare a couple of variables here. I'm going to call int mult1. So I'm going to use this as a multiplier. The multiplier, it will be +1 or -1, depending on the sign of the input. So I'll have int mult2, int mult3. So in my RAM, I'm going to figure out what the sign of the input is, basically. So if sign 0 equals 0, does that mean I'm adding or subtracting? Which one? Adding, yeah. So then mult1 should equal 1, right? I'm either multiplying the input by +1 or -1, depending if it's add or subtract. And then I can say else mult1 equals -1. And then I can do the same for sign 1. So that's it for my RAM. And then all we need to do is write the code for when the simulation starts. So the code is only one if statement, basically. If num inputs equals to 2, then my output equals to mult1 times input 1 plus mult2 times input 2. Else output equals to all of this plus mult3 times input 3. And that should be it. So we'll see if I've done this correctly when I try to compile the model now. So now that my code is written, my graphic is done, I can press compile here. And it says successful, so I think I did everything correct.
Back to the
Yep.
back to the C programming, the previous test for the programming for the C program. Back to the previous test. Yes. Yeah, I have one question about when you use the statement of the if.
Yeah.
Oh.
Yeah.
Yeah. Why don't you put the end for the end program?
I know.
If, yeah.
It's just our. It's not quite like C. It's close, but it's our own conventions.
Yeah. Not say for the.
Yeah.
For the,
So you don't need end if. When you read the manual, it will show you the different commands that you're allowed to do. And again, the manual, when you want to do this later, in the manuals tab, we have component builder tutorial, and this was gone. So now we have several different ones. The first one is the adder. There's one for an integrator, and then we have some power system ones too. So this is a power system component, the capacitor, multi-mass model, multi-thread component. So a tutorial on kind of how to build a relay, PMU shell component, and a generator control block. And I think shortly we'll be releasing one for a simple transformer. So I'm going to see if my system works now. I'm going to create a new file.
อ๋อคือว่าทำไมเวลาจบโปรแกรม if เนี่ย if loop เนี่ยปกติ
I'll save it in
อันนี้ก็ไม่ได้ใส่เองมันก็
my
คล้าย
folder.
คือเพราะว่ามันไม่เหมือนกับไอ้ภาษา C 100%ต้องไปอ่านเมนูดูดีประกอบดูแบบเมนูมา
Call it adder. So the first thing you have to do is get the component. So if you look in your RTDS user folder, under ulib, here's my component that I just made, multadder.def. So it's the actual component that we'll want to use is a .def file name. So in the library here, I can right click and I can say add component from the user manual or user library, ulib. This is one I made before, but I just made this one now. So I'll say open, and now I can bring it. It's a very big adder. So here my component is ready to use. So I can go to the controls library, and I can make some inputs. So I'll use some dials. So let's say I want to use all three inputs to test the full functionality. And we'll do add, subtract, add. That looks terrible.
When I modify the existing component,
Can you modify existing components? No. Sorry. We don't give access to our code for the simulator. It's all proprietary.
On the complex number, when they write and the C,
Complex numbers? Yeah, it's okay. In the when you add a variable, I can choose so your inputs and outputs can be if I add an IO point, I can choose a complex number. I think so, Dean. We can write complex number code in there, right? Yeah. It should be documented, I think. Yeah, you should be able to do that. And then I'll call the output simply output. So I want to change all my dials to real because my component is using real inputs, not integers. So my case compiled, so everything is still working. So in runtime, we'll actually see if the component does what it should. So first thing I'll add is a meter. I'm going to use a meter to monitor my output. And I guess I'll do minimum 0, maximum. The dials have 10 positions, so the max I can get out is 30. And I guess the minimum should be minus 30. And then I'll create my dials. Again, I'll use this pin. Dial 1, dial 2, dial 3. When you use the pin and do that, it lines them up nicely at runtime. Okay, so when I start my case, what should my output be? Based on this plus minus plus. What do I expect to see on my meter? Yeah. So this doesn't look good, does it? So something in my code is not correct. 3 minus 1 is 2, plus 2 should be, yeah. So this is good because now we can debug what the problem is. Add, subtract, add. So I'm going to have a look at my code again. Alright, so I have my mode 1, mode 2, mode 3. Sign 0 is 0. I have 1, minus 1, 1, minus 1, 1, minus 1. I think I need another if statement in here because I'm assigning mode 3 to sign 2, but I'm not, if I only have 2 inputs, I'm not using that third input. So let's say if num equals to 3, okay, so I'm going to cheat. It's a utility we provide, but it's up to the customer to work with it. I know, but we don't have anything like that. Sorry? Oh. Oh, I have two equal signs here. Right? I only need one. In the if statement, I should have two, but not when I'm assigning the variable. So I'll try compiling again. Compile my Java case. Hey, okay. It's always a simple error, but so everything seems to be working. Any questions about that? So the controls components are easier to do because they just have inputs and outputs and they execute every time step. So every 50 microseconds you're getting a new answer. The power system though, when you make a power system component, you're connected to other nodes of the power system. So if you make a capacitor, it's connected to, it could be connected to a breaker and a resistor on the other side. And you have to know, you have to understand the algorithm that the simulator is using in order to talk to the different components around it. Sorry? I do, but there is an example. I'm not going to do it because I don't think we have time, but you can follow it in the tutorial. It's pretty straightforward. It explains the theory and how to. Oops, not this one. The capacitor. So it explains how the system calculates the capacitor. Every power system component basically gets turned into something like this, a resistor with a current injection. Because then when we do the network solution, we can do it by doing nodal analysis throughout the entire network, and it's easier and faster for us. But the difficulty is coming up with the representation of this resistor and this current injection. So for a capacitor, you probably remember from the introduction course, the formula is well defined for the current across capacitor. And you might remember that we use trapezoidal integration. So what that does is turn a differential equation into an algebraic equation, which is a lot easier for the computer to solve. And we can represent these constants and these terms here by using a resistor in parallel with a current source. So this chapter walks you through how to do that and how to create the capacitor. No, you do, what happens is you do the hand calculations first to come up with your equations that you want to model. And then this equation, yeah, you always simplify down and you get a model that looks like this. And then it's easy to write the code for that. But this is a very simple model for a machine, for instance. There's a lot of work that has to be done in order to represent it that way accurately. Yeah, the transformer, I think we have a draft of the transformer tutorial, but we haven't released it with the software yet, probably the next release. But the transformer is a good example as well. Existing components? No. The code for our components is always hidden. You can use what there is though is existing functions, and you can make a function call that we built in to invert a matrix, right? So you don't need to write code to invert a matrix necessarily, because we might have a function available that you can just call in order to do that. So for instance, we have functions for absolute, arc post, arc sine, arc tan. different functions that are already available, so you don't have to write the code for it. You can just pass the variables to the function and it will return the output. So maybe we'll take a quick coffee break, and then we have to leave after lunch, so by lunch we should be finished. And I think after, I'll show you the website and how to do certain things, because I don't think all of you were here for the first course, so I'll show you how to ask support questions and things like that. So the scripting tutorial is chapter 7. I'm going to show you how it works, and then you can play around with it a little bit after that to change some things. So what I did is I went to the tutorial cases and I just copied chapter 7 into my directory. So I'm going to open up the draft case. So you can see chapter 7, it's the same circuit as chapter 2. So we have a source at one end, a transmission line, and some load over here. And in the middle of the transmission line, we have a fault branch. So the key things about this case is typically the length, where we apply the fault is set to a specific length on the line. And in order to change that, typically we have to recompile the draft case and then go start runtime again. So in this case we're using these things called draft variables. You can find them in the library. In the transmission lines, we have this draft variable slider. So by using this slider, we can adjust the values in runtime without coming back to draft. So we have a slider for the line length, and also a slider for the fault resistance. So for the fault resistance, we can see A phase to ground resistance. You always put a dollar sign in front of the variable. So our draft variable is called R on. So we have dollar sign R on. So that links this parameter to what the slider is set for. Same thing for B and C phase. In the transmission line, we have two calculation blocks, one for each section of the line. So here's our draft variable for the percentage of the length, dollar sign length, and that corresponds to this draft variable here, which is the length slider. And we've set it to, we can say percentage of the line, or 100 minus the percentage. So here we have just percentage, so 40, we have 40 here. That means the fault will be at 40% of the line looking from the left side. And in this box, we have 100 minus the variable, 100 minus this variable. So this section will be 40%, this section will be 60%, the way the variable is set right now. So this is my case, it's pretty simple. So I just have a plot which is showing my node voltages and then a fault control. So I can change the fault duration and I can select which type of fault I want to apply, A to ground, B to ground, C to ground, and I can change that. I'm getting this down here. Have you seen that before? D5 initialization. Sounds like why is it? Why are the lights on? Down here are my draft variable sliders that I can change. So right now this slider is set to 80% of the line and my fault resistance is 5 ohms. Oh, never mind. It's working. So sometimes you can see, sometimes you get some strange errors, but like anything else, if your computer is doing something funny, sometimes resetting it works. So I just powered the rack down and turned the power back on and now it's okay. So I can operate this manually, right? I can use my mouse and keyboard and make changes. I can set the type of fault that I want, A to B to ground. I can set my fault duration as 0.2, and then I can apply my fault and see my results. But if I want to do many different tests, it can take a long time to do it by hand. So we can write some code to do it automatically. So the first thing I'll do, up here we have a tab called script, and I'm going to say new script. There's already 2 in here which I'll show you, but I'll just make a new one. So I get this bar up here now, and I have several different options. I can record a script means I can start my simulation and change values and update plots, and it will write the code automatically for me, and then I can go in and edit it. So that's what I'm going to start to do. I can append, which means add on to the script, and I can also edit, and then these record and edit functions I won't get into now, but they're in the manual on how to use those. So I'm going to say record. So now I'm recording. I can start my simulation. I can log the plots. I'll change my fault duration to 0.1 seconds. And I'll turn a couple switches off. So I'll do a C to ground fault. I'll apply the fault. Oop, my plots are still locked, so I'll unlock and apply the fault. And then I'll stop the simulation and stop recording my script. So now if I go and edit, I've got some code that was generated. So you don't need to know so much. It tells you what the code is to do different things. So this suspend line is just saying wait. It's the time in between I did everything. So I pressed record, I waited 2.82 seconds, then I started the simulation. I waited 11 seconds. I locked the plots, master plot log state to 1. I waited another 3.5 seconds. Then I set my sliders to 0.1. I changed the switch values, A, B, or C, A, and B. And then when you push a button, there's 2 commands, so it tells you when you push it and when you release it. So when you're writing code, you need to do one after the other. You need to push it and then release it. Otherwise, it stays pushed. And then I unlocked the plots. I did the fault again, and I released the fault, and I stopped. So what I can do now is I can take these suspend statements out to make it go quicker. I'm going to take out this push that I did before I unlocked the plots because I can't see anything. And I'll save it. So now it should do everything really quickly. So once I start, I'll put a suspend command here for 5 seconds because I want the system to reach steady state before I start doing anything. So what I can do now is I can play my script and it should do everything I just did. If I move the sliders back to different values, it should change it all for me when I press play. So the script is running. It's waiting for 5 seconds, everything has changed, and here's my fault. So you can see it happened like that instead of me pressing all the buttons to do different things. So I have my results now. When you see that when we run the case, these draft variables, I can't change them because I can only change it when the case is stopped, because as soon as I stop it and change this value, it tells me that a preprocessor setting has changed because I changed the draft variable. So the case needs to recompile for that to get that information. And then my case will run now with the new value. So if I apply a fault, I should get some different waveforms. So that's the simple way, or a simple script. In this chapter, there's a script to do a little bit more. Batch mode.str. Script files have a .str extension, and when you edit them, it should open up in the text editor that you're using. So here I have my batch mode.str. You can see it's a lot longer. So I'll take you through what's happening here. At the beginning, we're declaring some variables. So we have JKI loop counter. So those are for pointers when we do loops, because when we write scripts, we want to do loops to do things multiple times. So either changing the resistance of the fault, changing the point on the line, and we can write for loops in order to run through all the testing. So here we're making an array of different values. So we're calling, here we've dimensioned some arrays: L length, line lengths, resistance, peak volts, and then we have an array for each type of fault. A, B, and C, and they each have three locations in the array. So line length, first fault we'll do is at 40%, the second fault is at 50%, the third fault is at 80%. So we're just filling up these arrays that we've created in the initialization. Same thing for resistance. The first fault will have 0.1 ohms. The second fault will have 1, and the third fault will have 5. And then we're filling up the different fault types. So for A, so when we have 0, we'll be doing an A to ground fault. The next loop, A won't be involved, so we're going to do an A to ground, and then when the counter increases to 1, we'll do a B to ground, and on the third one, we'll do a C to ground. So the reason we're using 1, 2, and 4 is because these switches, the switches for the fault logic, A goes from 0 to 1, B goes from 0 to 2, and C goes from 0 to 4. So if A is 1 and B and C are 0, we have an A to ground, because it's controlled by bit 1, so we have 0, 0, 1. B is controlled by bit 2, so we need 0, 1, 0, which is 2. And for a C to ground fault, it's controlled by bit 3, which is 1, 0, 0 in binary, and 1, 0, 0 is 4. So here's our first loop. We're using an arbitrary counter called J, and we're increasing it by 1 with each loop. So the second loop is to set the, first loop is to set the line length. So line length of J, so on the first iteration it'll be 0. Line length at 0, we'll be setting to 40%. The next time it goes through the loop, J is 1, and the line length will change to 50. The second loop sets the fault type. So we set the switch to the value of K. Again, K is going to be the same as J, so fault type A at 0, the switch will be 1, and the other two switches will be 0 and 0, so we'll have an A to ground fault in the first loop. Then we need one more loop to set the fault resistance. So again, we have 3 different resistances. 0.1 ohms, 1 ohm, and 5 ohms. So the first time through, it will be 0.1 ohms. And then this is the main part of the code. So remember, we changed 2 draft variables. We changed the slider for resistance, and we changed the length of the line. So we have to stop and start the case every time we change those. So we'll start the case, update our plots. We're recording this is what we call an external variable, and we're measuring N7 voltage in an array. And we're taking the maximum value of the voltage at that point. There's also commands for printing different things. So here we're going to print fault bus voltage equals to the value of the voltage of N7. So we'll wait for a certain amount of time, and we'll push and release the fault button, and stop the case. We can do other things like we can export plots to an Excel sheet or to a Word file and create reports as well. So I'll open that script file and I'll run it. So you can see we just did an A to ground fault with 0.1 ohms of resistance. Now we're going to do an A to ground, sorry, we changed the line length. Nope. We're changing the fault resistance. So we're on the C to ground fault now. We've just changed the resistance from 0.1 to 1. It's going to give us our fault. Now the resistance changes to 5. It's going to do the same thing and apply another fault. And now we're going to change the line length to 50. So then we do it all again with our line length at 50. So we're on A to ground, fault resistance of 0.1 ohms. That resistance will change to 1, and then to 5, and then it will go on to B and to C, and then change the line length again and do it again. So you can see we're doing a lot of different tests very quickly. It would take probably 10 times as long to do it by hand. So there's some cases where some of our clients have a case that runs for more than an hour, and it does thousands of different tests. And you can connect these script file cases to a real relay and see how the relay performs with all the different test scenarios. And you can create reports so that basically at the end of the day you can press play and go home and come back and everything is in a nice report for you to look at. So you can copy over chapter 7 to your directory and try and edit the script file a bit to do different things.
that the snapshot with the automatic class together for running in the runtime. I have one question about if can I directly define for the resolution of the line length something like example for 0.1 kilometer and starting from 0.1 kilometer to 100 kilometer. Can I do it?
Yep. I had an array, right?
Yeah.
Of different values. So 0 in the array was 40%, 1 was 50%, 2 was 80%. But you can make a bigger array and have every kilometer and fault. But it's specified in percentage, so you need to know how long your line is in order to do the calculation in your head, right?
Do we have some example?
Sorry?
Do we have some example?
It's the same thing as I just showed. Yeah.
Because in the case it's in snapshot with maybe pre-position for the fault data. And if I want to run so many points.
Yeah, so then you would just...
เนี่ยผมว่าเสมอแต่ถ้าเป็น snapshot จะเป็น snapshot ที่ว่ารันเรื่อยๆ snapshot ผมก็ต้อง
Test. Okay. So in your code, then you would you have line length. You can make this as long as you want. So then 3 could be, you could start at 1%, 2%, 3%. And just keep going. And then if you had, say you had 50 elements, then the loop where you're changing the line length, you just change this counter. You would put this as 50. So then you do the loop 50 times, and each time it changes your length. Which statement?
Why?
Why? While? Yeah. Yeah. There's while in there. Yeah. Yeah. Yeah, that's no problem. You can use while. It's pretty close. It's like C builder. It's pretty close to C, but not quite the same. How to get what? We can give you this, these scripts that we developed a couple of years ago. It's based on an IEC standard for distance relay testing. So it has a bunch of different cases. So, for example, they're actually pretty large, lots of code in these ones, but it's good to learn when you're looking at this. So, so in this example, we have functions. So a function called set source impedance ratio, so you can call the function instead of writing it in the main section of code. So here we're calling function call here. Instead of writing code to apply faults, we have a function for the fault to apply.
You just want a function?
Sorry?
You just want a function example?
No, he wants to know how to import a variable from the simulation on your script to like get data flow to compare something else over there. And that
Yeah, we're using these parameters. What we're doing is we're doing calculations in the script, and then we're plotting the results of those calculations.
Can you specify the parameter directly use some kind of
Yes.
some parameter equal to
So I think I can append to the script and I can add an external variable. So for instance, let's add a node voltage N1. Now if I edit at the bottom of my script, you can see I've added in this variable N1. So now I can take that N1 and do some, yeah.
can change
Sorry? So I wrote some of this, but not all of this, so I'm not quite sure what's happening, but like quickly. But I'm pretty sure we're taking this signal here, L1 and mean 10, and we're importing it into the script. And then when we do our fault cases, we're making this L1 and mean 10 an array with 8 different positions. And then for each fault type, we're picking, for each scenario, there's a bunch of different faults, and we pick the maximum or the minimum, or we calculate the mean, and then we store that result in one of the items of the array. So we'll have an array, once the testing is all done, the array will have 8 items, and same for this FLT location, it will have 8 items, and then we plot those 8 things on the graph here. So we're doing some calculations in the script, which we're then displaying on the plots in runtime. One other thing I'll show you quickly is, for those of you who haven't seen our website, internet doesn't seem to be working. Okay, so this is our website, and there's a tab here called Client Login. So there should be a username and password that you have to log into the website. So I'm logged in under our RTDS login, but there's some options on the side here. So if you have a component that breaks, you're covered under warranty for 1 year from the first course, which was in January. So you have warranty lasting until January 2014. And so if something breaks, you can go here to RMA request, and you can input your details, and we have a list of you should have a list of the components that you have at PEA. So this is all the components in the simulator, but when you log in under your website access code, you should have only the components that you purchased. So you can choose the component and the serial number, and then tell us what happened. And we'll get back to you with information on how to send the card back to us and repair it. If you ever send us an email, there's 2 ways to do it. You can email, the one address is support@rtds.com. So that email goes to a group of people that someone will email you back and try and give you a hand with any problems that you're having. You can sign up for email notifications. So we'll send you, we update RSCAD pretty often, maybe every couple months or more. So we can send you an email, we'll send you an automatic email when there's a new version of RSCAD on the website. And you get it from here in the download section. So here's all the latest versions of RSCAD. You can also download the release notes. So we have all these notes for version 3. So I can generate release notes in PDF. So I'll go 3.003 to 3.003. can download them. So I'll just open them up. So here's my release notes for version 3.003, the updates and the changes to the software. In downloads again, sometimes if we need to send you a file that's too large for email, we'll put it in your website login. So we can do that from the office back home. And you'll see a tab here, it'll say files for, I think files for PEA. And when you click on that, you'll be able to see the files that we've put in your login. Maybe it's a large presentation or some big simulation files or something. You probably remember when you install RSCAD on a new computer, you have to generate a key. So you come here to get RSCAD keys, and when you first install, you should have like a RSCAD directory, and you'll have a security directory, and you need to upload this .req request file, and then it will let you download a .key file, which you put in the same folder, and then you'll be able to run RSCAD. Typically, the firmware for the hardware, there is in tools firmware upgrade. I would say typically we recommend not to do anything unless we tell you, because it might break some things depending on your hardware configuration. So typically, if things are working as they are, then okay. One reason that you might upgrade your firmware is if we release a new processor card and you upgrade it and put the new processor card in your rack, that maybe the GT WIF card needs a firmware upgrade then to be compatible. So that's one circumstance where that could happen. But typically you don't need to change any of this, and all of your cards, they should be on the latest version of the firmware anyways. But if you ever have questions, just ask us before you make any changes. Maybe I don't know. Like we don't know what our next processor card will be or what's coming out next. We're always looking at new ideas for processor cards, but it depends. Typically, we try and have one generation back compatibility. So the previous processor card to the PP5 was called the GPC, and we made it so that a GPC can work in the same rack with a PP5 together. The older card before the GPC was called the 3PC, so that we said it can't work with the PP5. So I think maybe that the next processor card should be able to work with the PP5 as well. So we're always looking one generation back because we don't want to upgrade it and have everyone with PP5s kind of out of luck. So the nice thing about the GPC cards was since you can use them with the PP5 and they're fairly comparable, we have a hardware trade-in program. So if you're covered under maintenance, which you are for this year, but you can renew the maintenance and the warranty for software and hardware after the year is over. And if you're covered under those programs, then what we've done is, say you had 3 PC cards and you wanted to upgrade to PP5, when you trade in your 3 PC cards, we give you 50% off the new PP5 cards. So we have it's our hardware exchange program, which is a good incentive for people to upgrade. But with the GPC, it was nice because we could, typically the customers who had a mix of GPC and 3PC, we only took their 3PC cards and they kept the GPC and were able to use them with the PD5s. So we try and make things nice for the customers. I don't know if anyone else has that policy. If you get a new iPhone, Apple doesn't give you 50% off your old iPhone. I think that's about it then. Any questions? Yeah, for the watchdog timers on the IO cards. So yeah, where's that watchdog timer built into the width? So the amplifiers don't keep on. That's off the IO. Something that cuts off the amplifiers if something happens. Yeah, it's to protect your external equipment. If the simulation is stopped, the GTAO card is outputting 0. It won't continue to output voltage. Alarms? I don't think we have any other alarms other than the smoke detector. But if there's a problem, you'll typically have an error on the GT WIF card. There'll be a red light on the front.